Welcome to my classroom. In this chemical process calculation course, we have been discussing about material balance in unit operations. In that, we have seen numericals on various unit operations. In the previous lectures, we have seen numericals on material balance in dryers, and even we have calculated the recirculation rate of air, what is the fresh air, what is the humidity present in it, all that, right? So now we will do some numericals on another important unit operation called distillation. So I already have seen what is the basic principle of distillation in the introduction lecture to material balance and unit operations. Please refer to it. So now we will do some numericals on it. Essentially, in a distillation operation, based on the boiling point difference in vapor pressure, when a mixture of A and B are there, say A may be a more volatile component, B may be less volatile component. So we heat it to near to the temperature, boiling point temperature of A. So thereby the vapors of A is separated out, and so we get two streams. There is one input stream called feed, which contains more volatile component and less volatile component, and we have a distillate, a top product, where we collect more a stream which is rich in more volatile component A. Okay, and we get a bottom product called as residue, which is rich in less volatile component, that is B. So essentially A, B are there present in the feed in particular proportion. When it is a top product, there it is A rich phase, there is more volatile component is present predominantly, and the product B can be negligible or very less amount. Okay, we get a residue or bottom product where we have very negligible or less amount of A, and it is B rich phase. Okay, so that stream, bottom product stream is rich in component B. Okay, so with this we can do overall material balance and individual material balance for distillation operations. Okay, we have seen in petrochemical industries, the distillation is the mother unit where the crude petroleum is separated out into various products. Okay, so we are considering a simplest case, okay, where there is only one top product, whereas in case of distillation in petrochemical industries, refineries, we get a lot of product. I hope in some school onwards you have been studying about what are the fractionation during, what are the products that are obtained during fractionation, right? So that is the extreme case. So we will start with a simple numerical in distillation. Okay. So we are going to solve numericals on distillation. Okay, essentially a distillation unit, it may be a packed tower or plate column. So we have a fresh feed stream. We have a feed stream which contains A and B. As I said, A can be more volatile component, and B is less volatile component. B is less volatile. Okay, so we will have a top product. Actually, we will have a condenser, and some amount of the product will be recycled to the stream. So we will have a condenser here. So we will collect distillate. Okay, so distillate is D, and which will be containing both A and B, and it is a A rich phase. Okay, and in the bottom product we will have a reboiler. A stream is recycled, so it is called reboiler. So we will collect a bottom product called residue. Okay, so overall material balance is, what is overall material balance? Overall material balance for a distillate is F equal to D plus R. Okay, so this is overall material balance. If we write the individual material balance, individual material balance for A, let XF be XAF, XAD, XAW. So let the mole fractions are XF, XD, XW. For a binary mixture, A, B are there. So XA plus XB equal to 1, right? So that way we always skip the subscript A if it is a binary system. So I can say we consider a binary system of A and B. So this is sufficient that if you write simply x of xd xw in place of xaf, xad and xaw. Okay, so the mole fraction is equal to amount. What is the amount of solute A? Mole fraction multiplied by total kg equal to xd into d plus, we can write residue as W, okay, because why I have not used R is we are going to define something called reflux ratio here also, so that will be confused. So let R be reserved for residue recycle ratio. So let us use W for residue. So this is equation number 2. So using equation 1 and 2 we can determine the unknown parameters. Okay, for one of the example for A and B is A can be acetone, B is water. So in a mixture of A and B is the feed. So one of them is more volatile component, so that can be separated out. Okay, so let us do numerical on this topic. So take down this problem. A plant distills that is a chemical plant. A chemical plant distills 1000 kg of a 20% solution of acetone in water. 50 kg of pure acetone is lost to the water residue. The distillate contains The distillate contains 90% acetone and 10% water. Calculate the weight of distillate and residue. Report the composition table of F, D and R. Okay, so composition is what is mass percentage A and B. Okay, so that's what we have to do. I repeat, a plant distills 1000 kg of a 20% solution of acetone in water. 50 kg of pure acetone is lost to the water residue. The distillate contains 90% acetone and 10% water. Calculate the weight of distillate and residue. Report the composition table of feed, distillate and residue. Okay. As I said, let us use W for residue. So what is the basis for this problem? What is the basis? It is given 1000 kg of feed, right? So we have a basis given 1000 kg of feed. So feed is liquid, okay? Solution. So feed is liquid, so it is weight percentage. Okay. So we can assume it to be given percentage is in weight percentage. So we have taken a basis of 1000 kg and it contains let A be acetone, let A be acetone, B be water. Okay. So what is the amount of A? It is given, right? XF is given 0.20. Okay. So you can say what is the amount of acetone? Amount of acetone is equal to, this is F value, right? So amount of acetone is equal to XF into F. How much? 0.2 into 1000 is equal to 200 kg. So then you know what is the amount of water. Amount of water in feed is 1000 minus 200, which is 800 kg. Okay. So the feed contains 200 kg of acetone, and you can see that 50 kg of pure acetone is lost in the residue. Okay, residue contains 50 kg. Then what is the amount of acetone that is present in the distillate? So from given data we can write, it is given that 50 kg of acetone is present in W, that is residue. So therefore amount of acetone in distillate is 200 minus 50, that is 150 kg, right? That will be the amount of acetone present in the distillate. So what is the overall material balance? So if you have drawn the material balance diagram, if it is distillate, I have feed, I have distillate, I have the ammonia. So what is the 1000 kg? Out of which 200 kg is A, 800 kg is B. So W, it contains 50 kg A. So here we have 150 kg A. So that is individual material balance we have. So overall material balance is F is equal to D plus W. Okay. So we can say W is equal to F minus D, which is 1000 minus D. Okay. So this is overall material balance, and individual material balance already I have done it. That is XF into F is equal to XD into D plus XW into W. Let it be equation number 3. So what we have is, already we have calculated the amount, right? So that is 200 equal to, so this is given. So XD value is given. Okay, let me say it contains 90% A. So 0.9 into D plus XW is total amount we know. What is the amount it is present? 50 kg. Okay. So this equal to 150 is equal to 0.9 into D. Therefore D is equal to 150 divided by 0.9. How much? 166.67 kg. So that is the amount of distillate. Okay. So if this is D value, substituting in 2 we get a W value also. Substituting 4 in 2 gives us W equal to 1000 minus 166.67, which is equal to 833.33 kg. Okay, so F value we have, D value we have, W value we have. and we know the amount of acetone present in each stream. So we can make the table of composition. Okay, so we can make a table of composition. So draw a table. Okay, so what is the composition? We have A, acetone, and we have water. If A is acetone, B is water. Okay, so we have feed. We have seen that what is the total amount of feed? Total amount of feed is in kg. It is, what is the kg of feed? 200, 800. So what is the composition? Weight percentage. Okay, so weight percentage is 200 divided by 1000 into 100. So that is given data actually, right? 20% A and 80% B. So then we have distillate. What is the amount of distillate? Acetone present is 150. Water content is 16.67. Total is 166.67. Remember, actually we have calculated this. We know this. So 166.67 minus 150 gives us what is the amount of water. So amount of water in distillate is equal to total amount of distillate, that is 166.67, minus amount of acetone, which is 150. Okay, so that gives us 16.67, which we substitute here. Okay, so then what is the percentage of this? Total should be 100, right? So 150 divided by 166.67, how much? Percentage of A in D is equal to 150 divided by 166.7 into 100. So you get around 90%. Okay, so that is 90% of A, remaining is water, so 10% of B. Okay, so that is the composition of distillate, weight percentage. Similarly, we can write for residue. Residue W, what is the kg? You have seen that it contains 50 kg of acetone. So what is the amount of water in residue? 833.33 minus 50. This is our amount of water in this thing, which is coming out to be 783.33 kg. So 783.33 kg, total is 833.33 kg. So we can write the weight percentage in W. Okay, this is in kg. So 50 divided by 833. So percentage of A in W is equal to 50 divided by 833.3 into 100. So that you get around 6%. Okay, so the total is 100. Therefore this is 94%. So that is the composition table for feed F. That's what I asked, right, in the question. Feed F, distillate D, and residue W. So half of the data are given. We have determined the unknown data. Okay, so it is given feed contains 20% acetone, 80% water. So we know what is the amount of acetone in the feed, which is 200, and it is given that residue contains 50 kg of acetone. So input is 200, one of the stream contains 50, so the rest of the stream, that is other stream distillate, will contain 150 kg of acetone, which we determined first. Then using the overall material balance and individual material balance, we have calculated the value of D. So this is D value, this is W value, this is our F value, right? Which we have determined. So this way we should be able to solve distillation numericals. Okay. A binary mixture a binary mixture consists of 35% benzene and 65% toluene are continuously fed to the distillation column at a rate of 1000 kg per hour, whereas the distillate flow rate was 10% from the feed flow rate. The distillate, what is distillate? It is top product, contains 85% benzene. Calculate the quantity and composition of the waste stream. I repeat, a binary mixture consists of 35% benzene and 65% toluene are continuously fed to the distillation column at a rate of 1000 kg per hour. So 1000 kg per hour. A binary mixture consists of 35% benzene and 65% toluene are continuously fed to the distillation column at a rate of 1000 kg per hour, whereas the distillate flow rate is 10 kg from the feed flow rate, right? So how to solve this problem? So you can draw a block diagram. You can draw a block diagram. Okay, we have a feed. We have feed which is given as 1000 kg. So that is our basis. Basis is F is equal to 1000 kg per hour. Okay, so here A and B are benzene and toluene. Benzene and toluene are A and B. So it is given that it contains 35% benzene. So XF equal to 0.35, right? So XF equal to 0.35, and we have distillate. So what is our D? D is our distillate, and it is given that D is equal to 10% of F. So D is equal to 10% of F. What is that? D is equal to 10% of F, that is 100. Okay, so we have D equal to 100 kg, and top product contains 85% benzene, it is given. So XD is given 0.85. Question is, what is W, what is XW, right? So that is the question. So what is, if we have to, how to solve it? So we have first written the basis, what is A, what is B, we have written. Given data we have written XF, and it is given that D is 10% of the feed. D equal to 10% of F. So F value is 1000. So D is equal to 100 kg. So we got it. Okay. So what is overall material balance? Overall material balance for a distillation column is F equal to D plus W. Okay, F is 1000 minus 100 equal to W. So W is equal to 900 kg. Okay. Now what you can do is we can write individual material balance. So what is individual material balance? Individual material balance for A is XF into F equal to XD into D plus xw into w. Okay, so what is the, so let it be question number 3. So xf into f is, xf value is 0.35. So 0.35 into 1000 equal to xd is given 0.85 into 100 plus xw we don't know, w we got it. Okay, 2 in 3 we get the w value is 900. Okay, so this only unknown parameter is xw value, so we will get what is xw. What is that? xw value, please determine. $350 minus 85 divided by 900. How much? Use your calculator. 350 minus 85 equal to 265 divided by 900 equal to 294. So that is xw is equal to 0.294. So in terms of percentage, it is 29.4% A. So remaining is 70.56% is B. So that is the composition of W. So we can write W value is, we have determined W value. Okay. What is the W value? First we have to check W is correct or not. Go through the question again. Distillate flow rate was 10% from the flow rate. So that way we have 100. Product is 100 means W is 900 kg, correct. Okay. So we have, our answer is correct. We can always cross verify. Okay. So W is equal to 900 kg. Composition of W is, it contains A and B. A is quantity wise you can write, or you can simply composition is as, so percentage you can write. Percentage is 29.4, 70.6. Okay, what is the quantity also we can write if you want to write. Okay, total should be 900. What is the amount of A? Amount of A in W is equal to 0.294 into 900. How much? 0.294 into 900 equal to 264.6. 264.6. So what is the amount of B in W? 900 minus 264.6. How much? 635.4. Okay. Total is 900. Okay, this is the amount in kg. This is the percentage composition. Okay, so that's what asked in the question. So that is the answer for this question. Okay. remove the toxic pollutant from the flue gas that is leaving the system. Okay, so I have told you like some SOx, NOx, ammonia kind of products can be removed from the air that is leaving the system. Okay, so this absorption process, typically we use a solvent like water or any benzene kind of, so solvent is used. So this gas and liquid are come in contact with each other in a co-current fashion or counter current fashion. So the component A, solute component A present in the gaseous mixture is selectively dissolved in the solvent that is coming in contact with it in counter current fashion. So that way there is mass transfer taking place between gas to liquid. Okay, mass transfer is taking place from gas to liquid. That is solute A present in the gaseous mixture is removed, is diffusing into the solvent. Okay, so this kind of mass transfer usually takes place in a packed tower or plate column, which you will learn in detail in mass transfer 1. So in mass transfer course, you are going to learn about absorption. Now what we are going to do is understand what are the input, output, or how to do material balance in it. Okay, so typically in absorption process, there are two input. One is gas input and liquid input. Liquid may be solvent input. Okay, so there are two inputs and there are two outputs. So gas entering will be rich in A, solute A. So that may be a toxic component which has to be removed, right? So gas mixture rich in A will enter the system, and a gas mixture less rich in A, that is A free gas. It may not be completely free, but maximum amount of A will be removed from gas. Okay, so that way less a gas stream with less amount of solute A will be leaving the system. Coming to the other side, what we are sending in, we are sending in a solvent, which may not be, if it is fresh solvent, it may not contain any solute A in it, right? Mostly it is negligible if it is fresh. But if it is a recycled stream, there may be some amount or a small amount of A present in the liquid stream entering the system. But what happens to the liquid stream that is leaving the system? It is absorbed the solute A from the gaseous mixture, right? So that way it will be rich in solute A. So we have a liquid stream entering which has very less amount of A or negligible amount of A, and we have a liquid stream leaving the system which is rich in A. So this is what happens in a typical absorption column. So we have a gas stream entering, gas stream leaving, a liquid stream entering, liquid stream leaving. So there are two input, two output. That solute, so that we can easily write the overall material balance, two input, two output, and individual material balance for solute A can be written. Okay, so that way we'll be able to solve the material balance numericals in absorption. Okay, so we'll solve the numerical on it. Okay, we have an absorption column. So we have gas stream G with solute A is entering, and we have gas stream. So let it be 1, let it be 2. So G1 is the gas flow rate, G2 is the gas output. Okay, so we have, it contains A. So we can say mole fraction of A here. So actually for gas phase, we will write Y as a mole fraction. So we can have Y2 and we will have Y1 as the corresponding mole fraction. Okay, Y1, Y2. Similarly, we will have a liquid stream L2 entering, and which has mole fraction of solute A, which is X2, and we have a liquid stream leaving, which is L1, and let the solute present in it be X1. So we have X1, X2 are solute composition, or the mole fraction of solute, in liquid streams L1, L2 respectively. Okay, let Y1 and Y2 are mole fraction of solute A, here also solute A in gas streams G1, G2 respectively. So the overall material balance is G1 plus L2 is equal to G2 plus L1. The individual material balance is Y1 G1. This is overall material balance. This is individual material balance for A. Okay, so Y1 G1 plus X2 L2 is equal to Y2 G2 plus X1 L1. So this one represents bottom conditions, 2 represents top conditions. Okay, that assumption we are making. 1 represents bottom conditions, 2 represents top conditions. G1 is entering, G1 is gas entering the system, right? L2 is liquid entering the system. L1 is liquid leaving the system. G2 is gas leaving the system. So with this, we will able to solve the numericals in this absorption. Okay. Now take down this problem. In the manufacture of HCl, a gas containing 25% HCl gas and the rest air is obtained. In the manufacture of HCl, a gas containing 25% HCl gas and the rest air is obtained. This gas is passed through an absorption column in which 98% HCl is removed. The gas enters the system at 322 Kelvin and 743 mm mercury and leaves at 300 Kelvin and 738 mm mercury. Calculate volume of gas leaving per 100 liters of gas entering. Okay, that is first part. Second part is the composition of gas leaving the system. C part is the weight of the HCl removed per 100 liter of gas entering. Okay, I repeat, in the manufacture of HCl, a gas containing 25% HCl gas and the rest air is obtained. This gas is passed through an absorption column in which 98% HCl is removed. The gas enters the system at 322 Kelvin and 743 mm mercury, not 7434, 743 mm mercury, and leaves at 300 Kelvin and 738 mm mercury. Calculate the volume of gas leaving per 100 liter of gas entering, the composition of gas leaving the system, the weight of the HCl removed per 100 liters of gas entering. Okay. So this is a numerical we have. So first let us make a diagram for it. Okay. Let me check the meeting is being recorded and presented. Yes. So how to solve this problem? So let us make a block diagram. Okay. So we have 100 liters of gas with 25% HCl entering. So that is our basis. So what is our feed gas? Okay. So we have G entering 100 liters. It contains 25% HCl. So that is our gas entering the system. We have to make an absorption column. We have a gas entering. We have a gas entering with 25% HCl. Okay, so bottom condition 1, top conditions 2 means we have G1. Okay, so we have 100 liters of gas entering. So it is given in volume and temperature and pressure conditions are given. It enters at 322 Kelvin, 743 mm mercury. So why these conditions are given? Because G is given in volume. To convert it into moles, we will use this ideal gas law equation, right? So that is the purpose. So that's similarly G2 value is given, and G2 temperature is given as 300 Kelvin, 738 mm mercury is given. Okay, we have liquid entering, which is L2, and we have liquid leaving L1. Okay, so what is the amount of HCl removed is we can be calculated. Okay, so let it be x1, let it be x2. That is mole fraction of HCl in. So our solute here A is HCl. Okay, A is HCl. So we can write its composition. All this can be solved. So we can do this problem. So this is a gaseous system, right? So since it is a gaseous system, we can do the problem in terms of molar basis. Okay. So how to do it in molar basis? Let us see. Okay. So what is the basis given here? So I repeat, in this problem, gas is entering with 25% HCl and at a temperature of 322 Kelvin and 743 mm mercury, and the gas is leaving at 300 Kelvin and 738 mm mercury, and the composition of HCl in the gas entering is given as 25% HCl, and it is given that volume of the gas leaving per 100 liter of gas entering. So that we have to determine, and we have to determine what is the amount of HCl removed per 100 liters of gas entering. So basis is 100 liters of gas entering. So that will be our basis. Okay, so we can solve the problem now. So how to solve? So we have 100 liters of gas. So we have V equal to 100 liters, and we know N equal to PV by PV equal to nRT, ideal gas law, right? So we have temperature, pressure, volume. Okay, so volume is given in liters, convert it into meter cube, and R value we know 8.314 kilopascal meter cube per kilomole Kelvin. Temperature is given, right? 322 Kelvin. Pressure is given 743 mm mercury. So convert to kilopascal. 101.325 kilopascal is equal to 760 mm mercury. Remember, we have to always use this unit tally procedure wherever it is applicable. Okay, so you will get a pressure of, use the calculator, 743 into 101.325 divided by 760. How much? 743 into 101.325 divided by 760, which is 99.1. Okay, 99.1 or 99.06. So I will write 99.06, which can be taken as 0.1 also, right? So let me write with 2 digits correction. So we have pressure equal to 99.6. So we can find out the N value. So we have N kg moles. So please find out the N kg mole. N equal to pressure value. Pressure is 99.06 kilopascal into 100 liters, 100 into 10 power minus 3 meter cube divided by 8.314 kilopascal meter cube per kilomole Kelvin into 322 Kelvin. So we have Kelvin getting cancelled. Okay. So we have meter cube getting cancelled. Kilopascal getting cancelled. So we get answer in terms of kilomoles. So how much? Please use your calculator. 99.06 into 100 into 10 power minus 3 divided by 8.314 divided by 322 is equal to 3.7 into 10 power minus 3. Is that correct? 3.7 into 10 power minus 3, which is 0.0037 kg mole, or in terms, so it's very low value. We can even report as gram moles. How much gram moles? 3.7 gram moles. Okay, that is our N value. And it is, so in terms of mole basis, so whatever percentage given is 25% is mole basis only, right? So out of this, G entering is G1 equal to 3.7 gram moles. G1 is equal to 3.7 gram moles. So amount of the amount of HCl in it is HCl in G1 is equal to 25 percentage. 0.25 into 3.7. How much? So that much gram mole of HCl is present in the gas entering the system. So this is 0.925. Okay, so then what is the amount of inert air? Amount of inert air entering is equal to 3.7 minus 0.925. How much? 2.775. 2.775 gram moles. So that is the amount of, remember total gas is 3.7, in which 25 percentage is HCl. Therefore 0.75 percentage of 0.75 into 3.7 is 2.775. So that is the amount of air entering the system. Okay, I repeat. First, whatever pressure is given, 743 mm mercury, we converted to kilopascal. We converted the number of kg moles into gram moles. So we using PV equal to nRT. Okay, pressure, temperature, R value, and volume is given 100 liters. We converted to meter cube. So we obtained this much kg moles. So then among that, it is given that 25% is HCl, 75% is inert air. So we got the amount of the value, and it is also given that 98% of HCl is removed from the system. During absorption, what is happening? 98% HCl is removed. So HCl present in the feed is 0.925. So amount of HCl removed is equal to amount of HCl removed is equal to 98% of amount of HCl in G1 entering. So amount of G1 entering, right? So we can say that 0.98 out of 0.925 is removed. So which is equal to 0.907 gram moles of HCl. So amount of HCl removed is 0.907 gram moles. Okay. So what is the amount of HCl present in the air that is leaving the system? We have drawn the diagram, right? Block diagram. So 25% HCl amount is 0.925. Out of that 0.925, HCl removed is equal to 0.907. So then what is the amount of HCl present in this gas stream leaving the system? 0.925 minus 0.907. 0.925 minus 0.907, right? So that is the amount of HCl present in gas leaving the system, that is G2. Okay, in G2, what is the amount of HCl present? You can subtract this to find out. 0.925 minus 0.907. How much? 0.925 minus 0.907 is equal to 18 into 10 power minus 3, which is 0.018. Okay, 0.018 gram moles. So this is the gram mole of HCl that is present in the gas stream. Okay. So what is the total G2? Whatever is the inert air that is entering, whatever is the amount of inert air that is entering the system, you can see that amount of inert air entering is 2.755, right? 2.775. So what is G2? G2 is equal to inert air. Whatever inert air entered will be present in the G2 also, right? So HCl in G2. So this amount is 2.775 plus HCl present is 0.018. So we have total amount equal to, please add this, 2.775 plus 0.018 is equal to 2.798 gram mole is the 2.798 gram mole is the G2 value. What is G2? This is the gas stream leaving. So what is the question? First question, what is the volume of the gas leaving per 100 liter of gas entering? So what it is question, what we have determined is in gram moles. So what you have to report is in terms of volume. So again, for that we will make use of the conditions, right? N is given, N value you have, right? So we can use PV equal to nRT. So you can find V equal to N2RT by P. So N value is 2.798. R value, temperature and pressure is given. You can determine the G2 value, right? So how to find G2 value? So we have V2 is equal to N2 value, that is 2.798 multiplied by R value is 8.314 kilo. This is kg gram moles, right? Kilopascal meter cube per kilomole Kelvin into temperature is 300 Kelvin, pressure is 98.391 kilopascal. How we get this? So again we have to convert the pressure given 738. P2 is 738 mm mercury. So divided by 760 mm mercury into 101.325 kilopascal will give us pressure value 98.39. Okay, so what you will get is, so kilopascal getting cancelled, gram mole, kilogram mole is there, convert to kg mole into 10 power minus 3 kg mole. So Kelvin gets cancelled. So what you get is volume in meter cube. Okay, so whatever you get, you'll get 70.8 meter cube. So in terms of liters into 10 power 3, So that is around 7,800 liters. Okay, so that is almost 71,000 liters is the answer. So this is the answer for part 1. Okay, so question is, what is the composition of gas leaving? So that is simple, you can do it. Composition of B part answer is composition of gas leaving. So you have air and you have HCl content in it. So air is 2.775, HCl is 0.018, total is 2.793, percentage you can express, right? These are gram moles. 2.775 divided by 2.793 is around 99.36 percentage. HCl is 0.64 percentage. Total is 100%. So this is the composition of gas leaving. Remember, air is unaffected and it remains the same. That's why we got this 2.775 from the inlet gas. Okay. So that is the answer for second part. Okay. So what is the third part question? Third part is, what is the amount of HCl removed? So that we have already calculated. Answer for C part is amount of HCl. So that we have calculated, right? 98% of whatever is entering. So which is equal to 0.907 gram moles. So that is the answer for C part. Okay. So that's how we have to solve this problem. So what we have done essentially a gas stream is entering. A gas stream entering the system is given. Okay. So I'll explain it here. So a feed gas of 100 liters is given, which has 25% HCl. First, what we have done is this 100 liters we have converted to gram moles. To convert that to gram moles, we have used ideal gas law. So for that, pressure and temperature are given. This 743 mm mercury we converted to kilopascal. Similarly, for leaving stream, we have 738 mm mercury, that also to be converted to kilopascal. So using PV equal to nRT, we can convert this gas 100 liters into what is the number of gram moles. Okay, because it's not in kilomole because it is very small value. Okay, so 3.7 gram moles. So that gram moles contains 25% of HCl. So we determine the quantity of amount of HCl in it. Then we have calculated it is 25%. So the remaining is inert air. So 2.775. Same amount of air is leaving the gas system, right? So that way we have calculated then. Okay, so that way we got the final answer for each case. So we have calculated the answer for all the parts. Okay, so amount of HCl removed is 0.907 gram moles. Composition is 99.36% gas, air, and HCl is 0.64%. Okay. Hello friends, the extraction is one of the unit operation in chemical industries. There are two types of extraction. Leaching, which is solid liquid extraction, that is we have a solid from which we use a third component like solvent is mixed to leach out one of the constituent from it. For example, oil seeds, we have so many oil seeds, edible oil seeds and non-edible oil seeds. So for example, sunflower, rapeseed oil, tamanu oil. So like that we have so many seeds like groundnut. From all these solids we can extract oil from it. So from these oil seeds we can extract oil from it. So that process is called leaching, which is solid liquid extraction. There is one more extraction called liquid extraction, where a mixture of A and B is there, from which we add a third component C to selectively take out one of the component present in the liquid mixture. So that is liquid extraction. We will do a numerical in extraction. So for in any unit operation, two things we should do. For actually, if it is a solid, what we have to do is we have to consider weight percentage. For liquid and solids, we will be considering the percentage given as weight percentage. For gases, we will consider it to be mole percentage if it is not mentioned, but if it is specifically mentioned, the same thing we have to make use of. Okay, also we have to draw a figure with the data given in the form of block diagram, right? So same thing we are going to do in this numerical also. Take down this problem. A batch of soya bean containing 18% oil, 10% water. A batch of soya bean contains 18% oil and 10% moisture. It is to be treated with 10 pure hexane to give a solution containing 25% oil and 75% hexane, and a residue containing 0.5% oil and 20% hexane. What weight of soya bean is required to give 1000 kg of solution? So we have to make a 1000 kg of solution. Okay. Then there are two ways of solving the problem. As I said, it is easier when the composition is there. We used to choose a basis according to the composition, and finally whatever is the required data, we can finally multiply it in the ratio method. Okay, so there are two ways. Otherwise, directly also you can assume 100 kg of solution as the basis and proceed. But when you have a composition, it is always better if you choose a basis of solids. Okay, so that's what I have told you. Solid basis is considered because weight percentage is given. Okay, so this extraction. So typically a extraction we can draw a block diagram. A block diagram is you will make a diagram. This extraction. So there are two inputs and two outputs. Okay, so we have a seed which contains 18% oil, 10% water, right? And we have hexane entering into the system. There are two output. One is solution with rich oil. That is, see, remember here 18% oil, even though it is 18% oil, so even though it is 18% oil, it is in solids. Okay. Whereas here 25% oil is in solution. So here we get 25% solution. So here it is 18% oil in the solid. Okay. So this is solid. So this is liquid solution, right? So we have a residue. It is given that residue contains oil of 0.5 percentage. Hexane is pure. So that means oil is 0, right? So these are the conditions we have. So we can solve the problem. Okay. So we can take a basis of 100 kg of soya bean and proceed to solve this problem. Okay. So this is our system. Okay. So what we can do is we can arrange a basis. So what is the basis? Basis is 100 kg of soya bean. It is given that it contains 18% oil, 10% water, remaining are inerts. Okay, so what is the remaining percentage? Is it 72, right? Total will be 100. So in terms of kg, how much we have? Oil is, we have oil which is 18 kg. Here we have considered 100 kg soya bean seed as the basis. So we have 18 kg oil and remaining 80 inert, let's say inert plus water is 82 kg. Okay, so that is our basis. So we have 18, we have a feed 100 kg of soya bean which has 18 kg of oil and 82 kg of inert plus water entering into the system. So we have one input. Whatever is the inert, will this inert contain the solution? No, this solution contains only 25% oil and hexane 75%. So that means inert plus water whatever is present in the seed will be present in this residue. Okay, so that means this residue will contain this inert plus water. So the same amount of inert plus water which whatever was entering, that is 82 kg, will be present in the residue. That we should understand. Okay, residue will contain 82 kg of this one, but the residue composition is given. Residue contains 0.5% oil and 20% hexane. Okay, so that can be sorted out. Okay, so we have 20. So this oil residue contains 0.5% oil, 20% hexane, and inert plus water 82. This is amount, not percentage, right? So whatever is the amount of inert and water that is entering in the seed, that will be present in the residue. That is the concept we should make use of. Okay. So that is what is the percentage in residue. Let me say we have residue which contains 0.5 and 20, that is 20.5. So what is the remaining? 20 means 80, 79.5, right? So 100 minus 20.5 is 79.5 percentage, and we have 79.5. Let residue be R. Okay, 79.5 percentage of R is equal to 82. Therefore, R is equal to 82 divided by 79.5 percentage means 79 by 5 by 100, right? So this is 82. Therefore, R is equal to 82 divided by 0.795. This is equal to, what is the value? 82 divided by 0.795 is 103.14. 103.14 is the value. Okay. So we have residue value of 104.34. So what is the amount of oil that is contained in the residue can be determined now, because 0.5 percentage of R is the oil content in residue, right? So oil in residue, oil content in the residue is equal to 0.5 percentage of R, that is 0.5 by 100 into 103.14 kg. So what is the oil content in residue? Use the value 0.5. So we have already 101.14 answer in the calculator, multiplied by 0.5 divided by 100 equal to 0.515. 0.515, so which can be written as 0.52. Okay, 0.52 kg of oil is present in the residue. I repeat. So first, what we have understood is, from the given condition, we have gone for a basis of 100 kg of soybean seed, which contain 18% oil and 10% water. Remaining is inert content. So out of only 18 is our oil. So remaining is whatever is the amount of water and inert that is present in the seed. This solution does not contain any water or water. Right? Clearly mentioned, it is 25% plus 75%, total 100. So that is containing only oil and hexane. Solution contains only oil and hexane, whereas residue contains 0.5% oil. So the rest of the thing is going to be the inert and water, right? Understood? So the inert and water is there. So whatever is the amount of inert and water present in the seed will be present in this residue also. So that is the point we get taken. Since we have taken 100 kg of soybean oil, so out of 100 kg, 18 kg is oil. Inert and water is 82 kg. So the 82 kg of inert and water is present in the residue. And what is its percentage? Percentage is oil is 0.5, hexane is 20. So 20.5 is the percentage of oil and hexane. So the remaining percentage, 100 minus 20.5 is the percentage of inerts and waters. Right? So that amount we have, and the quantity also we know 82 kg. So we have 79.5 percentage of R equal to 82. Therefore, R is equal to 82 divided by 79.5 by 100 which is 103.14 kg. So then now we know what is R value. Now we can find out what is the amount of oil present in the residue. That is 0.5 percentage of R. So 0.5 by 100 into 101.14 gives us what is the oil present in the residue. Oil present in the feed is 18 kg. Oil present in the residue is 0.52. So that what will be the oil present in the solution? Let S be the solution. Okay. Let F be the feed. Let H be the actually this is solvent. Let me say put H itself because we are using Xn. Okay. Residue already we have assigned R. So please define the terms. Let F is the feed of oil seed. H is the hexane. S is the solution. These are kgs, right? In kg. And R is the residue in kg. Okay. So accordingly, we have got the value. So amount of oil present in the seed is 0.52 kg. Okay. So amount of oil present in the residue is 0.52 kg. So out of 18 kg entering in the feed, 0.52 kg is present in the residue. The remaining amount will be present in the solution. So we can write amount of oil in the solution is equal to amount in feed minus amount in residue. So these are individual material balance, right? So what is the amount present in the feed? So this equal to 18 minus 0.52. So which is calculate the value 18 minus 0.52. 17.48, right? So what you get is 17.48 kg is the amount of oil present in S, right? So and the percentage is given, right? So from the diagram we have 25% oil, 75% hexane. So now we can find the oil amount we know, so we can find out S from it, right? 25% of S is equal to this. Okay, amount of oil is equal to amount of oil in S is equal to 25% of S. Okay, that is 0.25 S. Okay, and this is equal to 17.48. So we have 0.25 S equal to 17.48 kg. Therefore, S is equal to 17.48 divided by 0.25, this much kg. How much? 17.48 divided by 0.25 is equal to 69.92. 69.92 is the S value. Okay. 69.92 kg is the S2 value. Okay. So this is the value of S. Okay. So we got S value. Now we can find out the we can find out how much 69 S value is for 100 kg of oil seed. When we use 100 kg of oil seed, when we use 100 kg of oil seed, how much solution we are getting? 69.92 kg solution is obtained, right? Here question, what is the question? Go through the question. For 1000 kg of solution, what is the amount of solids required? Check the question once. What weight of soya bean is required? Check. What weight of soya bean is required to give 1000 kg of solution? Right? So what weight of soya bean is required to give 1000 kg of solution? Okay. So now it is only proportion. As I said, we have done the problem with respect to basis of oil seeds. So now what we want is to obtain 1000 kg of solution. How much kg of oil seed is required? Right? So we have x into 69.92 is equal to 1000 into 100. So we get x equal to 1000 into 100 divided by 69.92. Okay. So what is the x value? This is the calculator. 1000 into 100 divided by 69.92 equal to 1430.21. Okay. So we get value of 1430.2 kg. So that is the required answer. Okay. So that is the answer. Take down the next problem. The waste acid from a nitrating process contains 23% HNO3 nitric acid, 57 percentage sulfuric acid, 57% H2SO4 and 20% water by weight. This acid is to be concentrated to contain 27 percentage of HNO3, 60 percentage of H2SO4, this acid is to be concentrated to contain 27% nitric acid, 60% sulfuric acid by the addition of concentrated H2SO4 containing 90 percentage of HNO3. Calculate the weights of waste and concentrated acids which must be combined to obtain 1000 pounds of desired mixture. Okay, this is a mixing problem where we do blending. Okay, different composition of material liquid solutions are mixed. Okay, so this is a very simple material balance problem. We should be able to solve it. Okay, so what is the composition we are going to get? Okay, so we have a nitrating process. So this is not a chemical reaction involving a waste acid is coming from the nitrating process. So we have somewhere some other process taking place from which a waste acid is coming, which contains 23% nitric acid, 57% sulfuric acid. Okay, and 20% water by weight. This acid is to be concentrated to contain 27% nitric acid, 60% H2SO4. Okay. This acid to be concentrated to contain 27% of nitric acid, 60% of H2SO4 by the addition of concentrated sulfuric acid. One second. Concentrated sulfuric acid containing 93% H2SO4 and concentrated HNO3 containing 90% HNO3. Okay, so that is a small correction. Okay, we are going to mix concentrated H2SO4, which is concentration is 93%. We have going to add concentrated nitric acid, which is 90% concentration. So we are having three input here. What are the three input? Waste acid, which contains all the three, both the acids. Then pure concentrated acid, which is 93%. Another concentrated nitric acid, which is 90%. So there are three input, and we are going to get a final solution. Okay, so final solution will have 27% and 60% of sulfuric acid. So that is the numerical we have to solve. Okay, so how to solve that? Let us proceed. So we have the problem beside us. So we have to make a block diagram first, right? So we'll go with the diagram. So what is the diagram? We have somewhere we have a nitrating plant, nitrating process. Okay, it has nothing to do with us. From this we are getting a waste oil. Okay, so what we get is waste acid, and which contains, let me say ABC. What are ABC? A is HNO3, B is H2SO4, C is water. Okay, so we have waste acid coming from the plant. Okay, so we have a mixture. You can say blender. Blending means mixing of various things. So we have waste acid coming into the system. So then what we have is we have HNO3. Okay, so we have HNO3 with a particular composition, that is 90% HNO3. Remaining is water, you can assume that. Okay, and then we have pure concentrated sulfuric acid, which has 93% sulfuric acid. Okay, so that is concentrated. We have concentrated sulfuric acid, we have concentrated nitric acid and waste acid. So there are three input streams are there. Okay, and there is one output, that is our desired product, desired mixture, and this quantity is given, right? Desired mixture quantity is given to be 1000 pounds. Okay, 1000 pounds of this thing is to be done. Okay, and composition is also known. What is the composition? Desired thing. In addition, what we should get is this is to be concentrated to contain 27 percentage HNO3, okay, 27 percentage A, 60 percentage of H2SO4, that is B. Remaining is water. The remaining you can calculate 6 plus 2 8, 87, 90, 87 plus 3, 90 plus 10, 30. So we have 13 percentage of water. So this we are calculating. This is given. This we have calculated by total should be 100 percentage. So we have calculated what is the water percentage here also. Right. So here waste stream feed containing it is A is 23 percentage, B is 57 percentage, C water is 20 percentage. Check the total 7 plus 3 10 100. Okay, so these are the streams. So what is the X? That is, this is the X kg of waste acid is entering, and what is the amount of this thing? At X is the amount of this thing. Y, that will be Z. So I am assuming three terms here. X is the pounds of, because it is given pound, you can even directly do it in pounds. Okay, how much X is the pounds of waste acid. Let Y is the pounds of concentrated HNO3, let Z be the pounds of concentrated sulfuric acid. So we have to find out these values, right? Calculate the weights of the waste and concentrated acids which must be combined to given. So we have to find out what is X. We have first assumed let X equal to pounds of waste acid, Y is pounds of concentrated nitric acid, Z is pounds of concentrated sulfuric acid. We have to find what is X, Y, Y. Okay, we have to determine X, Y, and Z. Okay, so that is the question for us. So what we can do is we can write the material balance. So here what is 90% nitric acid means what is the water percentage here? Water is 10 percentage. Here what is the water percentage? Water is 7 percentage. Here water is 10 percentage. Okay. I repeat, concentrated nitric acid is 90%. That means remaining 10% is water. Concentrated sulfuric acid is 93%, which means remaining 7% is water. Okay. So with all these terms, we should be able to solve the problem now. So what is the overall material balance? Overall material balance is input equal to output, right? So we have taken a basis of decide product equal to 1000 pounds, right? So what are the inputs? We have X pounds plus Y pounds plus Z pounds should give 1000 pounds. That is our overall material balance. Overall material balance is X kg of waste acid, Y kg of concentrated nitric acid, and Z kg of this thing. Okay. Now, what is the material balance for sulfuric acid? Material balance for sulfuric acid. Okay. So what is the material balance for sulfuric acid? What is the material balance for nitric acid? Material balance for nitric acid is the respective composition. In the feed, it is containing 0.57, right? 0.57 X plus in Y, what is the percentage? In Y, it is 0. The amount of sulfuric acid in Y is 0. plus 0.93 Z equal to, what is the amount of this thing? It contains 60% sulfuric acid. Product contains 60% sulfuric acid. This is the material balance for this thing. So which is equal to 600. We have 0.57x plus 0.93 Z equal to 600. So that is the individual material balance for sulfuric acid. Similarly, what is the material balance for nitric acid? Nitric acid is A. A is nitric acid, right? So it has 23% in the feed, waste oil. So therefore you can write 0.23x plus amount in this one is 0.9, right? 90%. 0.9 into Y plus 0, because the amount of nitric acid in the concentrated sulfuric acid is 0, is equal to the product contain 27% nitric acid. Therefore 0.27 into 1000, which is 270. So we have 0.23x plus 0.9y equal to 270, which is individual material balance for. So these are all individual material balance for sulfuric acid and nitric acid. So we have three equations. Okay. So solve these equations simultaneously, you will get the answer. So what you have is, you have x plus y plus z equal to 1000. Okay. So then we have y plus z equal to 6 and some terms, right? So accordingly we have three expressions. Solving this, we can obtain the answers. You have to find out the x, y, z values. So we have three simultaneous equations. Solve this equation simultaneously, you will get this value. Okay. So can we rearrange this equation number 2? So this equation 2 can be rearranged to express z in terms of x. What is that? 600 minus 0.57x. See, remember you can solve it in different ways. Okay, depending upon your skill level, you can solve it differently. I'll do one basic method. 600 minus 0.57x divided by 0.93 is, we can rearrange to write what is z, right? Similarly, 3 can be rearranged to write what is y. Y equal to 270 minus 0.23 x divided by 0.9. Okay, we are rearranging the equation number 3. We get what is y value. Okay, so let it be equation number 4. Let it be equation number 5. So in here you can replace y. Here you can replace z. Substituting 4 and 5 in 1, you will get the value of x. Substituting 4 and 5 in 1, what we have? 1 x plus y plus z equal to 1000, right? So we can write x plus, what is y? 270 minus 0.23x divided by 0.9 plus, what is z? 600 minus 0.57x divided by 0.93 equal to 1000. So can you simplify to get what is the value of x? Simplify and report the value of x. Okay, so what we will get is x value is equal to 415.45. Okay, So once we get this value, we can substitute this value. Let me give this number 6. Okay, once we have x value, we can plug in equation number 4 and 5. Substituting 6 in 4 gives us y value. Substituting 6 in 5 gives us, substituting 6 in 4 gives us z value. Okay, and substituting 6 in 5 gives us y value. So these are our pounds, because we have assumed 1000 pounds as the final value, right? So you will get the y value. Y value you will get, substitute 600 minus 0.57 into 415.45 divided by 0.93. Divided by 0.93 gives us the value of y, which is, value of z, which is 390.5. Similarly, the y value you will get, y value, if you substitute this in this equation, 270 minus 0.23 multiplied by 415.45 divided by 0.9 gives us the value of 200.7. Okay, so x plus y plus z total should be equal to 1000. Okay, that also you can verify. Remember, verification, x plus y plus z equal to 1000. You add these three, if it is coming to 1000, then we have calculated correctly. So we have the values reported here. Okay, so you can, what you have to verify, better way of verifying is doing material balance for tie element. We have defined what is tie element, key component. Tie element is water, because water is present in all. Okay, in all the products it is present. We can say that for water you can do the material balance. In the feed, in x it is 0.2, okay, 0.1 y plus 0.07 z is equal to 0.13 into 1000. That is the individual material balance for key component water. Okay, so substituting this, you can verify if LHS value. So this is your, RHS value. Calculate LHS, calculate RHS. If LHS is equal to RHS, so our calculation is correct. Okay, so you should be getting around 130 lb on both sides. Okay, left hand side and right hand side, you will get around 129 or 130 pounds. 129 or 130 pounds you will get in left hand side as well as right hand side. So that will make us problem correct. Okay. Okay, so in this, what we have done is unit operations. Particularly, we have considered in this lecture what we have discussed. We have considered a distillation column. We have considered absorption column. We have considered an extraction unit, and finally we have considered a blending unit. So this blending problem is most common in competitive examinations. Okay, so that way is important. Please practice similar numericals. You can find the similar numericals in all our textbooks like Himmel Blow, Button Vora, okay, Binay Datta, all these textbooks you can refer. Okay, so you practice numericals on this type. We will have all each type of problem, because next topic is unit operations, multiple unit operations, material balance in multiple unit operations. So what we are so far what we have done is individually we have considered a distillation column, we have considered absorption column, we have considered a extractor, we have considered a blender, like that, right? So what if they are present in series? We have a feed entering a absorption distillation column. The product that is coming out of the distillation is sent as the feed to absorption column. The product that is coming out of the absorption column is sent to some dryer, like that, if they are in series. So they are called multiple units, right? So this is what an actual chemical process industry will look like, right? So that way we should able to solve numericals even when involving multiple units. So that is will be the agenda for our next lecture. So if you are thorough with this type of individual units, it is easy for us to go for solving the numericals in multiple units. So there also what we have to do is, first we have to consider a basis. We have to properly take whether percentage givens are in weight percentage or mole percentage or volume percentage. Okay, so then we have to look for the key component. So minimum present, where minimum entry, minimum output, such component we should identify. Whatever component present in all the units, we should do overall material balance. We have to do individual material balance for components, and we will be able to solve the numerical circuit. So that will be the agenda for our next lecture. Okay, thank you for joining my classroom. If you have any doubts, please contact me. Okay, thank you.